In this video, I'd like to continue with where we left off on propionyl-CoA, which is made in the last round of beta oxidation. So let's take our mitochondria here. Let's draw our mitochondria right over here. And then we have the inner membrane right over here, right? And so if we take our propionyl-CoA, what's going to happen to it? Well, let's first remind ourselves of what happens in this process. Let's take an odd fatty acid. So let's take, let's say, a 17 carbon fatty acid. And this will get inside the mitochondrial matrix using the carnitine shuttle system that we talked about previously. And of course, it will produce some acetyl-CoA right over here, but it will also make propionyl-CoA in that last round, if you guys recall. Now, this propionyl-CoA is a 3-carbon molecule, and it will get converted into methylmalonyl-CoA. So during the first step, this propionyl-CoA will actually get converted into another molecule known as methylmalonyl-CoA. And this methylmalonyl-CoA is going to be formed via a carboxylation reaction right over here. So to make this reaction happen, we need to add bicarbonate, and we also need ATP. So this is the ATP portion. So we need some ATP to convert propionyl-CoA into methylmalonyl-CoA. Now, propionyl-CoA is a 3-carbon molecule, whereas methylmalonyl-CoA is actually a 4-carbon molecule. And the enzyme that's responsible for doing that is known as propionyl-CoA carboxylase. So let's actually write that over here. So we start off with propionyl-CoA, which we make during the last round of beta oxidation, and this will be first converted into methylmalonyl-CoA. And the enzyme, let's put that in green, is known as propionyl-CoA carboxylase. During the next step of this process, we're actually going to take that methylmalonyl-CoA. It's actually going to undergo a shift from the D form to the L form, and the L form of the methylmalonyl-CoA will actually be converted into a Krebs cycle intermediate known as succinyl-CoA. And in this step, we actually require vitamin B12. And by the way, during the first step, during the carboxylation step, I didn't mention that, but we needed vitamin B7 as the coenzyme. So let's write the next step down. Methylmalonyl-CoA will be converted into succinyl-CoA. And this is a Krebs cycle intermediate. And for this reaction, we need another enzyme. And this enzyme is called methylmalonyl-CoA mutase. And essentially, we're still at 4 carbons. Both methylmalonyl-CoA and succinyl-CoA are 4 carbons long. There is just some rearrangement of the atoms to go from here to here. And remember, the coenzyme, the vitamin that we need for this step, is vitamin B12. Okay? So succinyl-CoA is very, very important, and it can do a lot of different things. For example, it can be used to make heme, which is important in hemoglobin, as well as porphyrin rings, super important. it can also enter the citric acid cycle, as I mentioned, and be turned into oxaloacetate. And if you guys recall, oxaloacetate can be used in gluconeogenesis. What's going to happen is that this oxaloacetate is actually going to be converted into malate, right? So it's going to be converted into malate in the mitochondrial matrix and then leave into the cytoplasm as malate and then be converted back into oxaloacetate in the cytoplasm of the cell where it can be used for gluconeogenesis. So this oxaloacetate can be used in gluconeogenesis. And then, of course, succinyl-CoA can enter the citric acid cycle and make ATP. Let's illustrate the roles of succinyl-CoA over here. It can be used to make heme. It can also make oxaloacetate, as I mentioned, which can be used in gluconeogenesis to make glucose, GNG, gluconeogenesis. And it can enter the citric acid cycle. The interesting thing to realize, let's actually erase that. Right over here. Is that this propanyl-CoA, when it's converted into succinyl-CoA, it requires an ATP, as we saw in this process, right? And when this succinyl-CoA enters the citric acid cycle, it actually skips the production of 2-NADH. And if you recall, that NADH can be reoxidized to NAD in the electron transport chain to make 3-ATP. So if it skips the production of 2-NADH, it actually skips the production of 6-ATP. And since we needed 1 ATP to convert that propanyl-CoA into succinyl-CoA, and since we skip the production of 2-NADH, we're actually going to make 7 ATP less. And this is specifically when we compare a 17-carbon fatty acid to a 16-carbon fatty acid, where we make 8-acetyl-CoA. But here we make 7-acetyl-CoA and a propanyl-CoA, but that propanyl-CoA makes 7 ATP less. So therefore, a 17-carbon fatty acid will actually make 7 ATP less than a 16-carbon fatty acid. The next thing I'd like to do is have a look at what happens in the peroxisomes. So in the peroxisomes, you also have beta oxidation taking place. Let me actually draw a picture of a peroxisome. So let's make a peroxisome right over here. Let's say this is our peroxisome. And let's actually put some transport proteins right here. Now the peroxisome, unlike the mitochondria, is made up of a single membrane. It has transport proteins here, and it doesn't use the carnitine shuttle system. The steps are similar, but the first step is a little bit different. So again, we have our fatty acyl-CoA coming in from the cytoplasm to the peroxisome, and it's going to go again through one of these transport proteins. So that's pretty easy. We get it inside. We have our fatty acyl-CoA. This fatty acyl-CoA will then be oxidized during the first step, if you guys recall. And in this first step, we're going to make FADH2. So we're going to convert our FAD into FADH2. Okay? And during this same step, because we do not have an electron transport chain in the peroxisome, we cannot reoxidize it there. So what's going to happen is this FADH2 is going to go back to FAD. So the FAD still picks up the hydride ions to make FADH2 in this oxidation step. But the FADH2 normally takes the electrons to the electron transport chain where it's reoxidized back to FAD. But peroxisomes don't have the electron transport chain, so they cannot make any ATP there. What's going to actually happen is that the FADH2 is converted back to FAD, and it's going to give the two H's to oxygen to make H2O2, hydrogen peroxide. Hydrogen peroxide is toxic. It's dangerous. It can damage proteins and DNA. It's a free radical, right? So it's a free radical, so it can cause damage to the cell. But it does play a crucial role in function in the peroxisomes. But the peroxisomes can actually handle this hydrogen peroxide, because what they have is a special enzyme called catalase. And this catalase is going to break this hydrogen peroxide into half oxygen plus water. So they can tolerate high levels of this H2O2. Another big function of peroxisomes, other than making this hydrogen peroxide, which plays an important role, is that they break very large chain fatty acids into smaller fatty acids. So we're talking about long and medium chain. So they convert very large chain fatty acids into long chain fatty acids plus medium chain fatty acids. The very long chain fatty acids, think like 26 carbons, huge, and then they turn it into smaller ones, and these long and medium chain fatty acids can be handled by the mitochondria. So they will go to the mitochondrial matrix, handled in the mitochondrial matrix, where they will undergo beta oxidation, as we saw in the last video, and produce your acetyl-CoA, NADH, and FADH2, which can then be used over there in the electron transport chain in the inner mitochondrial membrane, right? And make your ATP. So these smaller fatty acids can enter the mitochondria and be used in beta oxidation to make ATP. Now there can be conditions where you actually don't make these peroxisomes. And in this case, you will not be able to break down the very long chain fatty acids into smaller ones, which can be handled by the mitochondria. So these very long chain fatty acids will accumulate, right, in the cells. And so you get an accumulation of these very long chain fatty acids. You can also have an issue with these transporter proteins on the peroxisomes, so they cannot let in these very long chain fatty acids. So again, they will accumulate. So either the peroxisomes don't function well, or these transporters are not functional. And now I'd like to talk about what can happen if you're missing the first enzyme of beta oxidation. The first step, the enzyme in the first step of beta oxidation. And this is known as MCAD deficiency, or medium chain acyl dehydrogenase deficiency. In this case, the enzyme responsible for the first step of beta oxidation is not functional. So these individuals cannot burn fatty acids, right? Inability to burn fatty acids, despite being able to bring them into the mitochondrial matrix. You still have the carnitine shuttle system, the CAT1 and CAT2, right? Those acyl transferases, the carnitine acyl transferases are working. You're able to bring that, you're able to get that fatty acyl-CoA in the mitochondrial matrix, but you cannot burn it because the first step is not working. The enzyme of the first step is not functional. There's a deficiency in that enzyme. So these individuals cannot burn fatty acids despite being able to bring them into the mitochondrial matrix. Since they cannot burn the fatty acids, what's going to happen is that these fatty acids are actually going to accumulate. So if one, you get an accumulation of these free fatty acids in the cell, right? So what you get is an accumulation of these fatty acids. So you get a higher level of them. And they can cause toxic effects, especially in the liver. So again, you get that lipid accumulation. And that can be toxic to the liver, for example. Also, since less beta oxidation takes place, we're going to make less acetyl-CoA. And since we make less acetyl-CoA, acetyl-CoA can be used to make ketone bodies in the liver. But since less acetyl-CoA is made, less ketone bodies will be made, right? Because acetyl-CoA is a substrate to make ketone bodies. So we get less ketone bodies, and therefore we get hypoketonuria. Okay? Lastly, beta oxidation is also used to fuel gluconeogenesis. So since we make less acetyl-CoA from beta oxidation, right? Beta oxidation makes a lot of ATP, whether it's directly from the rounds of beta oxidation where it makes your NADH and FADH2, or from the acetyl-CoA, which can then enter the citric acid cycle and make a bunch of ATP. So by having less beta oxidation taking place, you have less ATP made to fuel gluconeogenesis, and therefore you get less gluconeogenesis. As a result, you're going to get hypoglycemia because you're unable to fuel gluconeogenesis in the liver. So you get lower glucose levels because you're unable to release that glucose when the blood glucose levels are low. And this MCAD deficiency can cause a bunch of things, right? There's many symptoms that it can cause. It can cause a person to feel very drowsy, very tired, loss of fatigue, lethargy, and it can also lead to a comatose state and cause coma and even death in severe cases. Another thing I wanted to point out is you can also get hypoglycemia through a different mechanism. It turns out that acetyl-CoA is very important in activating a special enzyme known as pyruvate carboxylase. So if you have less acetyl-CoA, let's actually make this nice over here. If you have less acetyl-CoA being produced, you're going to have less activation of a special enzyme known as pyruvate carboxylase. And this is the enzyme that's responsible for converting pyruvate to oxaloacetate. And if you recall, pyruvate was converted to oxaloacetate, which was converted into phosphoenolpyruvate or PEP. And this was important in making glucose, eventually, in gluconeogenesis, through a bunch of steps. So by having less conversion of pyruvate into oxaloacetate, by having a reduction in this enzyme, we also make less glucose. and the outcome is the same. We get this hypoglycemia. Now, you may be wondering, well, what's the treatment for these individuals? Well, let me just erase some space right over here. So what is the treatment for these individuals? Well, the first thing is we want to give them a high carb diet because they're hypoglycemic. They have a low blood glucose. High carb diet and also high protein, right? And the other thing is we want to give them a low fat diet because the triglycerides that you get from food can be converted into free fatty acids. And because you already have an accumulation of free fatty acids, right, in the cells, this toxic accumulation, because we cannot break them down, we cannot burn them in the mitochondrial matrix, we don't want to give even more of these free fatty acids. So if you eat a diet high in fat, you're going to take in a lot of these, triglycerides, which can then produce a lot of these free fatty acids, which we don't want. So you want to give these individuals a lot of carbs, like a high carb diet and a low fat diet. And also you want to give them frequent feeding periods. Or you want to reduce the time between food intake, because these individuals are always they always want to consume food. They actually wake up to eat because they're hypoglycemic, so they wake up from their from sleep in order to consume more food. So you want to reduce the time between food intake and give them frequent feeding of a high carb diet, because they cannot make those carb, because they cannot make glucose, right, due to reduced gluconeogenesis, as there's nothing to fuel this process of gluconeogenesis, because gluconeogenesis is an anabolic process. As we'll see later, it requires 6 ATP, and because we don't have this ATP, because we're not burning our fatty acids, which remember give us 129 ATP per 16 carbon palmitic acid, we're not able to fuel gluconeogenesis. And also, we cannot produce acetyl-CoA, which activates pyruvate carboxylase, which gives us the oxaloacetate, right, which is important in gluconeogenesis. Oxaloacetate is converted into phosphoenol pyruvate via PEP carboxy kinase, phosphoenol pyruvate carboxy kinase, and this phosphoenol pyruvate can then be used to make glucose. This is really, really important because we're making that glucose to support gluconeogenesis in times of fasting when blood glucose levels are low. But since we're unable to do that because we're lacking the acetyl-CoA, which is needed to activate the enzyme to make oxaloacetate, we're unable to support that blood glucose homeostasis. So we get a state of hypoglycemia. And due to this hypoglycemia, these individuals wake up in order to feed. And so a high carb diet and the removal of fats, because we already have a buildup of fats, is very useful to support these individuals. Now this condition can be identified. It can be identified via newborn screening, right? Early in age, to see if you have the mutation that will give you MCAD deficiency. Because after all, this is an inborn error of metabolism, and these individuals have these metabolic issues. Anyways, I hope you found this video helpful. If you did, please like this video, subscribe, and leave your comments in the comment section below. And I'll see you in the next video. Thanks for watching.